My name is Dr. Rajendra Prasad. I am Assistant Professor in the Department of Mathematics, Government Degree College, Saidabad. Today, topic of my lecture is linear transformation. This linear transformation contains introduction and definition of linear transformation, definition with a property of linear transformation, range space, null space, or kernel, rank and nullity theorem, and some applications. Finally, we concludes and question and answer and some sources. Introduction. In this lecture, we will discuss about the linear transformation and their subspaces. Further, we will see some results and their applications. Linear transformation is connected with the linear algebra. In linear algebra, linear transformation are functions that preserve vector addition and scalar multiplication between vector spaces. Two fundamental subspaces associated with any linear transformation are first range space and second null spaces. We find that range space is subspace of codomain and null space is subspace of domain. These subspaces help describe the structure and behavior of the transformation. Linear transformation. This U is a vector space and V is another vector space. U represents the domain and V is codomain. And T is a mapping or transformation if satisfy this linear property. What is the linear property? Transformation of A alpha plus B beta transformation of A alpha plus B beta A alpha plus B beta is equal to A multiplied by transformation of A alpha and transformation of B multiplied by transformation of B beta. Definition. Let U and V be two vector spaces over the same field F. A linear transformation T from U to V is a function such that transformation of A alpha plus B beta बराबर A T alpha plus B T beta. For all alpha beta belongs to U. U is vector space. It is codomain of the transformation or mapping. Alpha and beta are vectors from this domain. And for all A belongs to F. F is a vector field and A comma B are scalars. This condition first is also called the linear property. If any function satisfy this property, that functions are linear. This function T is also called linear operator if codomain and domain are same. It means it is linear transformation from V into V itself. If it is linear transformation from V into V itself, it is called linear operator. We take some example of a function. Example is that so that the function T from V3 to V2 defined by the Tx comma yz is equal to x comma y for all x y z belong to R. Here function V3 is represents the domain of the function T, and V3 means it is a vector space of dimension 3, and here in the bracket R is a field, and in the codomain V2 represents the vector space of dimension 2 and R is field element of field. we will have to show that this function t is a linear transformation from V3 dimension of from dimension of vector space into a dimension of vector space 2. For the solution, take two elements of the vector space. First vector let vector alpha is equal to alpha 1, alpha 2 and alpha 3. Here alpha 1, alpha 2 and alpha 3 are component of this vector. There are three components because this domain is a vector space of dimension 3. And take another vector beta with three components, beta 1, beta 2 and beta 3 belongs to V3 R. And take two scalars a comma b which is belongs to the field element field R. Then if we show that T of transformation of A alpha plus B beta बराबर A transformation of T alpha plus B multiplied by transformation of B beta, then T will be linear. For this, we take T transformation of A alpha plus B beta. Putting the value of alpha and beta, we get transformation of A multiplied by alpha with three component alpha 1, alpha 2 and alpha 3 plus B multiplied by three component beta 1, beta 2, beta 3. Since we take the first component with together and second component in together and third component and with together, we get transformation A alpha plus alpha 1 plus B beta 1 comma A alpha 2 plus B beta 2 comma A alpha 3 plus B beta 3. Since our functions are given as T x comma y comma z is equal to x comma y, it means function gives the first and second component of the vector space. So by the given function we can write here T A alpha 1 transformation of A alpha 1 plus B beta 1 comma A alpha 2 plus B beta 2 comma A alpha 3 plus B beta 3 is equal to first component take according to function A alpha 1 plus B beta 1 and second component A alpha 2 plus B beta 2. Since in given function there is not taken third component, so we will leave the third component. And taking this result, we will pair in the bracket A alpha 1 from here and A alpha 2 from second component plus B beta 1 from first component comma B beta 2 from the second component. Taking the common A and B, first A from the first bracket and B from the second bracket, we will get A alpha 1 comma alpha 2 plus B in the bracket beta 1 comma beta 2. According to given function, first component and second component, these functions when we apply on vector space of 3 dimension give the vector space of 2 dimension. It means it give the 2 component only. So by this function we will write here alpha 1 comma alpha 2 is equal to transformation of alpha 1 comma alpha 2 comma alpha 3 plus beta 1 beta 2 is equal to T transformation beta 1 comma beta 2 comma beta 3. Thus we get A T alpha plus B beta B into T beta. Since this function given this function satisfy the property that T A alpha plus B beta is equal to A multiplied by T alpha plus B multiplied by T beta. This is a property of the linear transformation. So, given functions are linear transformation. Some property of linear transformation. Let U and V be two vector spaces where U is the taken domain as a domain and V is a codomain. Then transformation, take transformation T from U to V, and U and V are vector space over the field F. Then in this case, this transformation maps 0 to 0. It maps 0 to 0. Here in the left hand side, this 0 is from the domain. This is a vector, 0 vector from the domain. And 0 from, in the right hand side of the equal, this this 0 in the right hand side is 0 vector of the codomain or range, and this 0 is the 0 vector of the domain. It means this transformation map 0 vector onto 0 vector. It means image of the 0 vector is also 0 vector. And second property is the minus T alpha is equal to minus transformation of minus alpha is equal to minus transformation of alpha. And third property is equal to transformation of alpha minus beta is equal to transformation alpha minus transformation of beta. This alpha beta belong to the domain. Domain is what? Domain is the here vector space. And transformation of the linear combination of the vectors is equal to linear transformation of individual sum of the linear transformation of the field element is multiplied by the individual vector space. That means transformation of a1 alpha 1 plus a2 alpha 2 plus an alpha 1 is equal to a1 multiplied by transformation of a alpha 1 plus a2 transformation of a alpha 2 plus so on. In the last an is multiplied by transformation of alpha n, where a1, a2, an are the element of the field, and alpha 1, alpha 2, alpha n are a vector belonging to the domain. Range spaces of linear transformation. If the domain is vector space U and codomain is vector space of V, and here if you take linear transformation T from U to V, alpha 1, alpha 2, alpha m are the element of the domain, then its images T alpha 1, T alpha 2, T alpha 3, so on, T alpha n, these collections represent the images of the alpha 1, alpha 2, alpha 3 are called the range spaces. Definition of the range spaces. Let U and V be two vector spaces over the same field F and T be a linear transformation from U into V. Then range of T written as RT is the set of all vectors beta in V such that beta is equal to T alpha for some alpha in U. Thus the range of T in V is the image set of U under T. That is, it also can be written as RT is equal to, in mathematical way, RT is equal to T alpha belonging to the codomain such that alpha belongs to the U. This range space is also vector space, vector subspace of the codomain V. As a theorem, we will learn this result as a theorem. This theorem first is, let U and V be two vector spaces over the same field capital F, and T be a linear transformation from U into V. Then range of T is a subspaces of V. For the proof, let Y1, Y2 are two elements belonging to the range spaces, range set, range T, RT. Then there exist, if Y1, Y2 belongs to the range spaces, then there exist two vectors x1, x2 corresponding to these vectors y1, y2 in the U, such that y1 is image of any vectors x1 which is present in the domain U, and y2 is also image of any another vector which is present into U. For the proof, let AB, A comma B belongs to field element, that is A comma B, be any element of the field F. Then we have to show that RT is a subspace of V, that is A comma B belongs to field and Y1, Y2 belongs to range space, implies A Y1 plus B Y2 belongs to RT. It is a condition to be subspace of any vector space. We have ay1 plus by2, take the ay1 plus by2 is equal to A transformation of x1 plus B transformation of x2. y1, y2 is taken from here. Here we have supposed tx1 is equal to y1 and tx2 is equal to y2. From here we take tx1 is equal to y1 is equal to tx1 and y2 is equal to tx2. Since t1 and t is a linear transformation, so by the property of linear transformation we can write here transformation of ax1 plus bx2 is equal to a multiplied by transformation of x1 plus b multiplied by transformation of x2. But U is a vector space. It means domain U is a vector space, and x1 here in this expression x1, x2 are vector space of U, and A comma B are the field element. So ax1 plus bx2 belongs to U by the property of the vector space. Because U is a vector space, so it holds the property of vector addition and scalar multiplication. x1, x2 are vectors from the U, and A comma B are the field element. So scalar multiplication ax1 and bx2 and vector addition ax1 plus bx2 also belongs to U. If ax1 plus bx2 belongs to U, then its image is also in RT. That means we can write transformation of ax1 plus bx2 belongs to RT. That is, from the equation number second, here ay1 plus by2 बराबर transformation of ax1 plus bx2. Then transformation of ax1 plus bx2 belongs to RT. So here we take ay1 plus by2 belongs to RT. Why? Because transformation of ax1 plus bx2 and ay1 plus by2 both are equal from here. Thus we get, since A and B are the field element, y1, y2 are the element of the range spaces. So their linear combination, this implies linear combination ay1 plus by2 belongs to range spaces, and this is a condition for a vector space to be subspace of given vector space. Since y1, y2 are element of the range space and ay1 plus by2 belongs to, it means vector addition and scalar multiplication belongs to these spaces. So RT is a subspace. So RT, and it means range space, is subspace of the codomain V. It is proved. Second, kernel are null spaces. In the kernel or null spaces, there are element of the domain that has image as 0. If U is the domain of linear transformation T and codomain is V, and alpha 1, alpha 2, alpha 3, alpha k are element of this vector space vector space of the domain U, and let alpha 1 has image 0, it means transformation of alpha 1 is equal to 0, and transformation of alpha 2 is equal to 0, and transformation of alpha 3 is equal to 0, dot so on, transformation of alpha is equal to k is equal to 0. If all these images or some images has 0 images, then that element, collection of that elements are null spaces or kernel of the linear transformation. Here in the graph we have taken alpha 1, alpha 2, alpha 3, alpha k in the U which has image as 0. So in the null space or kernel of transformation, these all elements will be present as alpha 1, kernel of T is equal to alpha 1, alpha 2, alpha 3 and alpha k. Systematic definition, we can see here systematic definition. Let U and V be two vector spaces over the same field F, and T be a linear transformation from U into V. Then null spaces of T written as anti are KT. It is also denoted by KT. The written as anti is the set of all vectors alpha in U such that T alpha is equal to 0. 0 vector of V. Here in the right hand side of the equal, this is 0 vector of the V, it means codomain. That is null T is equal to alpha belongs to U, it means element of the all those elements belonging to U that has images 0. Alpha belongs to U such that T alpha is equal to 0, 0 belongs to the V. Null space of any linear transformation is also called the kernel of T, and also it is denoted by KT. There are some important result of this kernel. Actually, kernel of any transformation is also subspace of the domain. As a result, in the form of theorem 2, we see let U and V be two vector spaces over the same field capital F, and T be a linear transformation from U into V. From U into V, then the kernel of T are the null spaces of T is a subspace of U. For the proof, we take, since here we have to show that nullity, it means nullity of T is a subspace, we take two vectors in the nullity, and we will see that linear vector addition and linear combination also belong to this null space. For this, let x1 comma x2 belong to null spaces. If x1 x2 belongs to null spaces, then for 0 vector v, we have images of this vector x1 is equal to 0 and also image of the second vector x2 is equal to 0. Let a comma b be any element of the field f. If x1 x2 belongs to nullity and ab be field of element of the field, then we have to show that a comma b belong to f and x1 comma x2 belong to any nullity, implies ax1 plus bx2 belong to nullity, null space. For this, we will take transformation of ax1 plus bx2 and see, since t is a linear transformation, so we can write transformation of ax1 plus bx2 is equal to a multiplied by transformation of ax1 plus b multiplied by transformation of x2. And transformation of x1 is equal to 0 here, because x1 is an element of null spaces, and also transformation of x2 is equal to 0 because x2 is an element of the null spaces. So putting this value of the transformation of x1 and transformation of x2 here, we get a into 0 plus b into 0 vector, and finally we get 0 vector. So we get transformation of ax1 plus bx2 is equal to 0. It means element ax1 plus bx2 has 0 images. An element of the U which has 0 image also belong to null spaces. But use a vector space. Therefore, a comma b belongs to f and x1 comma x2 belong to u. Implies ax1 plus bx2 belong to u. It comes from the property of the vector space, because vector space holds vector addition and scalar multiplication. Here a is a scalar and b is a scalar. A is multiplied in x1 and b is multiplied by x2, and vector addition ax1 plus bx2, because ax1 is a vector and bx2 is a vector. So by the property of the vector space U, we get ax1 plus bx2 belongs to U, and ax1 plus bx2 belongs to U. And in previous step already we have given its images is equal to 0, and 0 is a, there was 0 was a vector of the range spaces T. Thus we get transformation of ax1 plus bx2 is equal to 0. By nullity definition, ax1 plus bx2 is an element which has image 0, so it comes in the set of null spaces, or ax1 plus bx2 belongs to nullity, and this is a condition for the to be subspace of a set of vectors. Thus we get a comma b belongs to f and x1 comma x2 belongs to null spaces, implies ax1 plus bx2 belongs to the null spaces. Therefore null space is a subspace of U. Next result is rank nullity theorem. This theorem related to the dimension of the null space and dimension of the range space. When U has finite dimension, then we get a relation between the dimension of null space, dimension of range space, and dimension of the domain of U. Here this alpha 1, alpha 2, alpha 3, alpha k has image 0, so This box represent the null space. And next, under the domain alpha k plus 1, k plus 2, so on alpha n, it means n minus k element. Total elements are vectors in the domain U is n. In n, 1 to k elements has image 0 image, but elements from k plus 1 to n has some images in the codomain. So here null space contains k elements and the range space has element n minus k. So null spaces are kernel of t is equal to alpha 1 alpha 2 alpha k, and range space of t is equal to transformation of alpha k1 and transformation of alpha k plus 2, so on transformation of alpha n. This picture represents the rank nullity theorem when U has a finite dimension. As a result, as a rank nullity theorem, before rank nullity theorem, we will see what is the dimension and rank of the null spaces. Since U is a vector space, null space is subspace of the U, and the null space has basis. In the basis of the null space, number of vectors in the basis of the null space is called the nullity of the transformation. And in the since range space is a subspace of the codomain V, and the basis number of elements in the range space is called the rank of the transformation. Here rank of the transformation is represented by rho t. This is rho, and the transformation of t is rho t, and is equal to dimension of the range space, and nullity is denoted by nu t, is the dimension of the range of t. Nu t is equal to also written as dimension of the null spaces. A rank nullity theorem is related from these relations between rank and nullity. It means dimension of null spaces and the range spaces. Let Un, as a result, in the form of the theorem 3, rank nullity theorem, let U and V be two vector space over the same field capital F, and T be a linear transformation from U into V. If U has finite dimensional vector space, then rank of T, it means transform rank of range space plus rank of null space equal to dimension of U. It means rank plus nullity is equal to dimension of U. Rank nullity theorem fails when U has an infinite dimension. In case of infinite dimension, this theorem does not hold. For the proof, already we have discussed about this figure. Here this represents alpha 1 alpha 2 alpha k null space, and this represents the range space. For the proof of this theorem, first we will suppose dimension of U is equal to n, because in the statement of the rank nullity theorem it is given that U has a finite dimensional vector space. If U is a finite dimensional vector space, then kernel or nullity is also a finite dimensional vector space, because nullity is a null space is a subspace of the U. Let dimension of kt या kernel या nullity is equal to dimension of nullity is equal to k, where k is a finite. Further, let B1, if it is a finite dimensional, it means this null space has in the basis of this null space are finite number of vectors which are linearly independent and having property of the spanning to this null space. On that basis, we take B1 is equal to alpha 1, alpha 2, alpha 3, so on alpha k be a basis of kt, where k is less than 1. Because dimension of any subspace is always equal or less than vector space, their vector space. Since B1 is a linearly independent subset of U, so it can be extended to form basis of set of U. With the help of B1 null space, we will try to write the basis of the U. For this, we take some another element alpha k plus 1, alpha k plus 2, so on alpha n, we will add in the basis of B1 to find the basis of U. If the alpha 1, alpha 2, alpha 3, so on alpha n, these are basis of U, then it has their images in the range space. As such, T alpha 1, T alpha 2, T alpha 3, so on up to T alpha n. This belongs to the range spaces. Now we will claim that the image vector T alpha k plus 1 and T alpha n are image of n minus k vectors is a basis of range space. To prove this theorem, we will show that the extra vector which are added by us, image of these vectors is nothing but they form the basis of range space of the T. To show that this is the basis of the range space, we will prove that this B3 is linearly independent and each vector of the range space P can be written as a linear combination of these vectors, or B3 span the range space of T, or linear combination of B3 is equal to range space. First we will show that B3 is a linearly independent. To prove B3, set of vectors B3 is linearly independent, let ak plus 1, ak plus 2, so on an are element of the field. As such, when we multiplied ak plus 1 by the image of the vectors alpha k plus 1 plus ak plus 2 multiplied by image of the alpha k plus 2 and so on, plus an multiplied by t alpha an is equal to 0. Actually, we will take this linear combination is equal as a 0, and we will show that these scalars which are used in this linear combination all are 0 to prove the linearly independent. Since we have taken this is equal to 0, operate transformation on this linear combination. When we operate transformation on this linear combination, we will get, since T is a linear transformation, the T ak plus 1 alpha k plus 1 plus ak plus 2 alpha k plus 2 so on is equal to 0, and these vectors belongs to the null space. Since every element of the null space can be expressed as a linear combination of its basis set B1, Therefore, for some scalars a1, a2, ak minus 1, ak belongs to f, we have linear combination of these vectors is equal to, since this is ak plus 1, ak plus 2, ak plus 1, alpha k plus 1, 2, so on, multiplied by scalars. These vectors, linear combination of the vectors, is an element of the null spaces. Here, this is an element of the null spaces, and basis of the null spaces is alpha 1, alpha 2, alpha 3, alpha k, and this is an element. So this element can be written as linear combination of alpha 1, alpha 2, alpha k, because this linear combination in the right hand side, this is an element of the null spaces, and this element can be written as linear combination of basis of the nullity, and basis of nullity, what are these are alpha 1, alpha 2, alpha k, which are already we have supposed. So taking the same side, all components, all expression, we get alpha 1 plus a1 alpha 1 plus a2 alpha 2, so on, minus a1 ak plus 1 alpha k plus 1 ak plus 2 alpha k plus 2, so on, an alpha n is equal to 0. But alpha 1, alpha 2, alpha 3, alpha k n, alpha n are basis of U domain, is linearly independent. Already we have know that alpha 1, alpha 2, alpha 3, alpha k, alpha n, these are basis vector of the U, and these are vector of basis, so they are already linearly independent. So linear combination of these vectors implies a1, a2, all scalars are 0. It means all scalars are identically 0. So a1, a2, ak plus 1, ak plus 2, an is equal to 0. It means we get ak plus 1, the transformation of ak plus 2, and some an plus t alpha n is equal to 0 implies ak plus 1, ak plus 2, an is equal to 0. Thus finally we get image vector, this linear combination of image vector, this implies when we take 0 implies the ak plus 1, ak plus 2 is equal to 0, an is equal to 0. So they are linearly independent. Now next we will prove that B3 span RT. To prove B3 span the range of T, that means linear combination of the vectors presents in the basis B3 is equal to RT, it means range space. For this we take any arbitrary element from RT, and we will prove that we will take any arbitrary element beta in the range space, and finally we will prove that this beta is nothing but this is a linear combination of the vectors t alpha k plus 1, t alpha k plus 2, t alpha k plus 3, so on, t alpha 1. For this, if you take any element beta belongs to RT, then there exists alpha belongs to U. It means if there are any vectors present in the range space, then corresponding vectors uh, corresponding vectors about this beta is also present in the another vector in U. It means corresponding to beta vector in the range space, there is a another vector in the domain alpha U such that T alpha is equal to beta. It means beta is image of any vector present in the U domain. Since B2 is a basis of U and also alpha belongs to U, therefore there exist scalars A1, A2, An belong to F such that alpha is equal to A1 plus alpha 1 plus A2 alpha 2 so on. It means alpha, if alpha is belongs to U, here U and V, if there is beta, then this corresponding this, there is another vector alpha, and this alpha can be written as linear combination of the vectors present in the basis of the U. Since in the basis of U we have vectors alpha 1, alpha 2, alpha 1, alpha 2, alpha 3, alpha k up to alpha n, and here we have taken alpha in U. So alpha can be written as A1 linear combination of alpha 1, alpha 2, alpha 3, alpha k, alpha n. And for images we operate T on both sides and we get T alpha, T of A alpha is equal to transformation of vectors in the form of this linear combination. So since T is the linear transformation, so it can be distributed over the scalars and vectors as such. T alpha image transformation alpha is equal to A1 multiplied by transformation of alpha 1 plus A2 multiplied by transformation of alpha 2 plus so on, and An transformation of alpha n. Since alpha 1, alpha 2 belong to nullity, in the basis of U, since in the basis of U there are elements alpha 1, alpha 2, alpha 3 so on alpha k plus 1, alpha k plus 2 so on alpha n, but these are elements in the basis is also basis of null spaces. Since alpha 1, alpha 2, alpha k minus 1 alpha k also vectors belonging to the basis of nullity, null space, so its images is equal to 0, and taking images equal to 0 in this expression and writing T alpha is equal to beta, as such we get beta is equal to A1 multiplied by 0 plus A2 multiplied by 0 plus so on plus AK multiplied by 0 plus AK plus 1 T alpha k plus 1 plus so on An T alpha An. Writing 0 in the place of the vectors T alpha 1, T alpha 2, T alpha k, we get beta is equal to AK plus 1 transformation of alpha k plus 1 transformation of AK plus 2 multiplied by transformation of AK plus 2 plus so on An transformation of alpha n. What represents this? This represents that beta is a linear combination of the images vector transformation of alpha k plus 1, transformation of alpha k plus 2, transformation of alpha k plus 3, and transformation of alpha n. It means beta is a linear combination of these vectors, these images, and since already we have supposed that beta is any vector of the range space, it means all vector or any vector of the range space can be written as the linear combination of these images vector. So these images vector are these images vector generate the each element of the range space. It means each vector of the range space can be written as linear combination of this vector, or we can say that uh, this set of vectors span the range spaces. This shows that B3 span the range of transformation, that is linear span of B3 is equal to range spaces. It means B3 is linearly independent and span the range spaces, so B3 form a basis of RT. Also dimension of RT already we have taken n minus k is equal to rank T. So taking the rank T minus k in the right hand side, we get rank T plus k is equal to n. The rank T plus k is what? K is a nullity of T, and n is what? N is the dimension of U. This represents the rank nullity theorem. This is the proof. This is the proof of the rank nullity theorem. We take this an example on the based on the null space, range space, and the rank nullity theorem. Take example 2. In the first example, we have seen that a mapping is linear transformation, and in this example second, we will take a mapping and we will find the basis of null spaces, range spaces, and also we will verify the rank nullity theorem taking the finite dimensional domain. We take the example 2. Let T from R power 4 to R3. R power 4 means domain is a vector space of the dimension 4 and codomain is a vector space of dimension 3. The linear transformation defined by the transformation x, y, z as T. Since domain is a vector space of dimension 4, so each element or vector of the dimension 4 has 4 component x, y as T is equal to range space. Since range space has dimension 3, so vectors in the range space have only 3 component: first, second, and third. First component is here given x minus y plus s plus t, and second component given x plus 2s minus t, and third component is x plus y plus 3s minus 3t. If our transformation is given, this transformation having domain is a finite dimension and dimension of domain is equal to 4, then first we have to find basis and dimension of the range space, and second find the basis and dimension of the null space or kernel. Third, verify the rank nullity theorem. For the solution of this type of the questions related to rank nullity theorem or null spaces or dimension or range spaces, first we take the standard basis of the domain. Since here standard basis of domain, since domain is vector space of the 4 dimension, so its basis, standard basis is equal to 1 comma first 1 comma 0 0, second component second vector 0 comma 1 0 0, 0, third is 0, 0, 1, comma 0, and fourth is 0, 0, 1. Since dimension is 4, so in its basis there are 4 elements. It means 4 vectors. All vectors are 4 components. The first as a standard basis, we always take 1, comma 0, 0, 0, 0, 1, 0, 0, and third is 0, 0, 1, 0, and fourth is 0, 0, 0, 1. Since for the range space, we take images of these vectors, and taking the image, we observe that that images must be linearly independent, and they have property, spanning property. If they are not linearly independent, we reduce the vectors linearly independent in the linearly set of linearly independent vectors. The image of these vectors, image of basis of r power 4, take the image of 1, 0, 0. Since our transformation is given transformation of x, y, s, t, and putting 1, 1 at the place of x, y, 0 at the place of y, and s, and 0, third is 0 here, putting at the place of s, and the fourth t at the place of t, 0 at the place of t. We get, when we put x is equal to this is x, this is y, this is s, this is t. When we put in this expression or this transformation, we get as an image 1, 1, 1. And when you put 0, 1, 0, 0 in this expression, we get -1, 0, and 1. When we put 0, 0, 1, 0, we get as an image 1, 2, 3. And when put 0, 0, 1, we get 1, comma -1, comma -3. Finally, we get 4 vectors in the range space, and that's vectors. These vectors are 1, 1, and 1, 1, 1, and -1, 0, 1, and 1, 2, 3, and 1, comma -1, comma -3. Since images are 1, 1, 1, 1, 1, 1, -1, 0, 1, 1, 2, 3, 1, -1, -3. But we are not clear that these vectors form basis of images or not. For this, we will check these vectors are linearly independent or not. To check the dependency of these vectors, we take in the form of the matrix, and we apply the echelon form. For the echelon form, taking the first element in the first column, we try to make -1, 0, 1, 0, and 1, 0. And taking these vectors, we will try to make 2 as a 0, -1 as a 0. For this, we apply row operation. R2 here is -1. We apply this operation. R2 indicates R2 plus R1. When we will add these two elements, it will be 0. When we apply this transformation, these operations, then it will be applicable all these elements -1, 0, and 1 also. And the first element of the third row, we will apply R3 indicate R3 minus R1. When we subtract 1 from 1, it will be 0. And third, when we subtract 1, this element 1 from 1, it will be 0. It means we will take operation R4 indicate R4 minus R1. And in second, we will take R3 indicate R3 minus R2, R4 indicate R4 plus 2 R2. Finally, we get a matrix in this form, echelon form, and this echelon form represents that there are uh, there are only two vectors which are ally vectors, which are linearly independent vector. It means in the basis of the range space is only two vectors, 1 1 1 and 1 comma 0 1 comma 2. It means dimension of the images RT is only 2 because there are two vectors in the basis of the image. Dimension of RT is equal to 2 and basis is 1 1 1 0 1 2. Second question was to find the null space and the dimension of the null space. For the null space, we take nullity. We use the definition of the kernel as nullity. In the null space, there will be present that elements of the U that have images 0. It means if alpha is element of U, then transformation of alpha must be 0 for the alpha belonging to the null space of the T. Using this definition, we take transformation of there are element x, y, s, t where there are any vector belonging to kernel. If these vectors are belonging to kernel, then its images is equal to 0. And using the function, since transformation of x, y, s, x, comma, y, comma, s, comma, t is equal to this expression having three component 1, 2, 3. And this will be 0. Since here 0 is dark and this 0 vector belonging to the range space, and range space has 3 dimensions, so its a 0 vector has 3 component 0 0 0. On comparing, we get a homogeneous system of the linear equation, and reducing the equation we get these are two equations, and here equation are 2 but variables are 4, so 2 variables are free and 2 variables are free. It means it has two solutions, only two vectors which are independent. So kernel and nullity has only dimension 2. For getting basis of the vector, basis of the null space, we take or we suppose that that's two free vector are s and t. These s and t will be linearly independent. Take the first s and t, first vector, take s is equal to 1 and t is equal to 0, and putting this s is equal to 1, t is equal to 0 in previous these two equation, s is equal to 1, t is equal to 0, we get x is equal to minus 2 and y is equal to minus 1. For second vector, take x is equal to 0, t is equal to 1, we get x is equal to 1 and y is equal to 2. After putting these x is equal to 0, t is equal to 1, previous these two equations, finally we get two vectors minus 2 comma minus 1 comma 0 and second vector is 1 2 0 1. These two vectors belongs to the basis of the null space, and dimension of null space or kernel is equal to 2. Third question was rank nullity theorem. Since rank is equal to 2 and nullity is equal to 2, the 2 plus 2 is equal to 4 and dimension of domain is equal to 4. So 2 plus 2 is equal to 4. This indicates that we see that the rank nullity theorem is verified. Rank nullity theorem says that rank of t plus rank of nullity of t must be equal to dimension of r power 4. Here 2 plus 2 is equal to 4. Some application, there are some application of this linear transformation, null space and range space. Just as such, first is solving system of linear equation. When we will solve the linear system of equation, there we can see that application of null space and range space. And in the data compression, in the data principal component of analysis data, in the data compression, we show that the data is range space represent the lower dimension, range space represent the data projected, and dimension dropped, null space represented the dimension dropped. It also represent the computer graphics rotation, projection, scaling, and all are linear and linear transformation. Null space tells that graphs are flattened. It means projecting 2 dimension into 3 dimension into 2 dimension. Another application in the control system, and in the machine learning we will see the application of these linear transformation, its and their property. Conclusion: after learning about the range space, null space and linear transformation, student may be able to understand the structure of the linear transformation and dimension theorem, geometrical interpretation of the graphs, application in advanced topics as such diagonalization, eigenvalues, eigenvectors, and singular value decomposition, and enhance their critical thinking and abstract reasoning. There are some questions for the student. Apply the linear transformation, property of the linear transformation and the property of range space and null space. We can solve this problem 1 to 5. Here are answer of these questions. Sources of this lecture. This lecture is first name of the book is Introduction to Matrices and Linear Transformation, Daniel T. Fink-Benier, and second is Algebra of Linear Transformation by Douglas R. Ferencik. Third is Linear Transformation, Examples and Solution by the Shah and Chaudhary. Thank you.